Hello, everyone. My name is Rizvee, and I'm a graduate research assistant at the I2S. And today I'll be talking about hierarchical Bloom filter-based framework for scalable authentication and tracking of ICs. So this is like an ongoing project, and it's a collaboration between University of Florida and University of Kansas. So in this project, what we're doing is we're trying to propose a framework that could be used to uh, track and authenticate integrated circuits in a supply chain format. So, okay. So talking about supply chains, if we consider a company, for example, Intel, which has produced ICs, and the ICs are circulating the supply chain and visiting each of the entities. And here, each of the entity is trying to enroll the records of the ICs in a traditional database so that they can track them at each end. But the databases, they're simply not a good choice because it's possible to tamper the data of an IC, and counterfeit ICs can enter the supply chain at any point. So the reason that they try to um, keep a record of the ICs is simply because one of the major reason is so that the counterfeit ICs cannot enter the supply chain. But it doesn't go a long way because since there is an issue of security of the ICs in the supply chain, because it is possible that a counterfeit IC can enter supply chain at any point of the cycle, uh, we would want a bit complicated identification tags, such as physical unclonable function. So a physical unclonable function is an intricate characteristic of IC, and it works like a biometric property. So instead of using any written ID tags to track ICs, we're using this PUF property of ICs, which makes the identification process much more secure. So what we're essentially doing is we're trying to organize the data or the IC data in a better way and in a secure way as well. So we're not the first one to do that. So yeah, so instead of like using traditional databases, there has been ongoing research on securing supply chain data using established state-of-the-art frameworks, such as the blockchain or Bloom filters. But the problem with these data structures is that you'll find it difficult to obtain a low storage and query efficiency. But there is another major problem, which is the noise handling property, which these data structures, they don't have. And why do we need it? Because uh, in like conditions, whether in different weather conditions, puffs can change slightly and introduce noise. So since it's possible that it could introduce some noise at any point of the supply chain, we would have to build something that would authenticate the ICs having noisy data. So we need to deal with the noisy data. So that's why we're proposing a persistent hierarchical Bloom filter. And this framework actually organizes and secures the data in a better way. That's what we're claiming. So before learning about persistent hierarchical Bloom filters, let's just go through the Bloom filter. Okay, so a Bloom filter is a probabilistic data structure that is used to test whether an element is a member of a set or not. So consider this example. In this figure, we have two operations of Bloom filters. So the first one is enrollment, and the second one is query processing. In the enrollment, before enrolling the data, we initialize a bit array and put zeros into all these positions of the array. And during enrollment, if we have a set of data, For example, if we have X1, X2, and X3, and so on, we put these data into a hash function, and the hash function generates a random output. And the random output number is basically nothing but the index number of that bit array. So we simply go to that index and flip the bits from 0 to 1. For when we query the data, if we find similar data, we borrow that hash function, and for the same data, we will definitely get the same output of the hash. So we just simply go to that bit array and check whether the bit array element is 0 or 1. Since it's 1, then we can say that it passed the membership test. But we have one data, which is XY, which is not a member of the set. So, and how do we know that? Because it's generating 4. And when we go to 4, we see that there's a 0. So this is not a member. So this was the Bloom filter. And this one is the hierarchical Bloom filter. So in a hierarchical Bloom filter, we have multiple Bloom filters that are arranged in a hierarchy. And we have on level 0, we can have a single Bloom filter. And on the preceding levels, we can have multiple ones. And what's the benefit of that? So if we want to enroll, for example, a string S0, S1 till S5, and on the first level, we can see that the Bloom filter enrolls the string altogether. But on the preceding levels, we have split the strings into multiple segments and then input them into the Bloom filters. So in the final level, we have granular detail of the string, and that is getting input into the Bloom filters individually. So what is the benefit here? So for example, even if when we're querying, if there is, suppose the string, there's a change in 5, and for example, we have S6. So on the first level, it won't get authenticated, but on the second level, it would when we're querying, because S0, S1, S2, S3, they're not changing. And on the last level as well, we will have at least 4 Bloom filters that are authenticating our string. So even if there's noise introduced, we will still have our Bloom filters authenticating our string. So this is our proposed framework, and we have arranged this hierarchical Bloom filter into multiple levels again. And this time we have associated them with time. So this is like a binary tree structure, and we have assigned a time period for each of the hierarchical Bloom filters. For example, whenever our puff responses are getting enrolled, let's say that we want to enroll, something got enrolled between day 65 and day 128. So our HBF, I'm not sure if you can see it, but yeah, the red marking is the HBF where our puff responses are going to be stored together. And this is how it goes until level 6, where we have granular level details on the puff responses. So coming back to the supply chain perspective, this is a schematic of the supply chain where the manufacturer is at Kansas City, and the supply chain expands up to Philadelphia, passing through every entity and its supply chain cycle. So as I mentioned, like every entity should maintain a PHBF. That's what we're calling it in short, to get the records of the ICs that they're handling. So the entities that are maintaining the PHBFs are connected to a secured centralized server
which constantly updates the ICs that are on their entry, so that anyone can have access to the records, anyone within the entities or the components of the supply chain. So as for the results, we measured the performance of our system in two divisions. The first type is the authentication performance. This is measured to know how our framework is identifying the puff responses of the ICs. This way, we know that the rate of authentication, even when there are noises within the query data. And the second type is the measure of the scalability of our framework. Like when we try to increase the input parameters to a greater value, we try to know how it's performing in terms of lookups and storage. So we measure the authentication performance using the receiver operating curves. And this actually shows that we can tune the parameters of our framework. If we do that properly, it's possible to achieve 100% authentication rate, even when we have query set that has noise incorporated. So these graphs are actually showing that FAR and FRR rate is 0 in all of them, all of the experiments we set. The threshold of the hierarchical Bloom filter, when we set them to 5 in every case. So each of the experiment is done on like different query sets after enrolling, and the query sets, how we generated them with a ring oscillator based puff in like 100 degrees and 75 degrees Celsius. And for the C and D, these two query datas were generated synthetically. So the scalability performance, it may not make a lot of sense, because when we try to calculate the overheads, we can see that there are a lot of dependencies which we have to consider to calculate the overheads. And these are the parameters, and these are the other data structures that we compared our proposed PHPF with. But this graph should make sense a little. So yeah, so the output shows the results in terms of like storage on the upper row and the query time in the lower row. And the one that is in the orange is actually the efficiency and scalability of our system. So we consider 3 parameters as our input, which is like location, time, and number of ICs. And we kept any 2 of them constant at each time and simulated our results with the remaining one. So you can see that in the upper row, in every case, our data structure is performing better, and like in terms of saving storage for larger inputs. And the second row actually depicts the time which is saving while performing queries, even when the query inputs are large. Yeah. Yeah, we're done. Do you have any questions?
That time. Any question?
Has this work been published?
So it's been submitted, but yeah, we're actually trying to reiterate through these formulas again. And it's been like submitted for a year and a half, and for some reason the publisher couldn't find any reviewers to review them. Yeah, so we're reiterating through these formulas again to see to make sure if there's like any problems or not. Yeah. All right. Yeah, sure.
If there is the counterfeit device introduced in any stage of this supply chain,
Yeah.
what do you expect?
So we can directly address the remarked ones and the cloned ones. So for this is the same reason why we're using physical and clonable functions, because for the cloned ones, you cannot just mimic a particular IC's signature. So the cloned ones, they're like straight away there, we're gonna like find them. For the remarked ones, so we're also trying to maintain a database that we're selling. For example, when it goes to the customer's end, we're keeping a database to track that as well. Whenever there's a remarked one or a recycled one comes in again into the system or into the supply chain, we're just gonna go through that database. And then if we find that, we can say that that's a remarked one or a recycled one.
And you have, where do you get the data from?
So yeah, so the data was collected from ring oscillator. Ring oscillator puffs. Yeah, it was generated in our lab. So it was done by one of my colleagues.
There's no data set available from the different suppliers and.
No, unfortunately not. Yeah. Sure.
It is acquired. How would you differentiate between an original and a clone one?
So the thing with a physical unclonable function is that you cannot clone a signature. It's like your face biometric is not clonable. Maybe if the face biometric is clonable, but your fingerprint is not clonable, right? So that's the same thing with physical unclonable functions also, because an IC has a unique signature, and the physical unclonable function is that signature. It's like the fingerprint, so it's not clonable.